In this video, we're going to talk about continuity. Specifically, our objectives here are going to be to define continuity at a point, to discuss and analyze continuity of polynomials and rational functions, to discuss limit laws of composite functions, to discuss continuity on an interval and define all appropriate intervals of continuity, to discuss continuity of functions involving roots, transcendental functions, and inverse functions, and to learn the intermediate value theorem and discuss how it applies to real-world situations. The intermediate value theorem is also sometimes called the mean value theorem, depending on your textbook. It will be used, those two terms will be used interchangeably. Mean means in the middle, intermediate means in the middle, so they are equivalent names for the same thing. So let's go ahead and look here at this first part. Our outline here, we're going to define continuity at a point. And to do that, we're going to have to know what limits are, which is why we discussed limits. We're also going to have to know about the existence of a point there. There's going to be three cases of discontinuity that we're going to talk about. We're going to create a checklist for determining continuity at a point. There's going to be a three-part definition, and we're going to actually use that three-part definition to tell when something is discontinuous. It's going to violate one or more of those three conditions. We're going to talk about continuity rules. We're going to discuss continuity of a polynomial and rational functions. I've already alluded to that. We're going to discuss continuity of function composition, going to define continuity on an interval, discuss continuity at endpoints and midpoints, to discuss continuity of other important functions like functions involving roots and transcendental functions. So the concept of continuity is a very important one in calculus. We can't talk about derivatives until we talk about continuity. We can't talk about antiderivatives until we talk about continuity. And derivatives and antiderivatives are the two big parts of this class that we're going to talk about. Both of them are built on the idea of continuity. So before, you likely thought of continuity as the ability to trace or draw the graph of a function without lifting your pencil up off the paper. That's kind of the layman's way of defining it, but we're going to define it more technically, more correctly, more mathematically, so more precisely. So we'll define continuity more precisely using limits, and we'll make a distinction between continuity on an interval versus continuity on a function's domain. So let's go ahead and get started here. So continuity at a point, let's start there, because we have to start with the discussion of continuity around a single point. So a function f is continuous at x equals a if the limit of f of x as x approaches a is equal to f of a. So when does the limit exist? Let's remember that. So the limit exists when the limit as x approaches a from the right of f of x equals the limit as x approaches a from the left of f of x equals L. L is a finite number. It's not positive or negative infinity. We're going to cheat, and we're going to talk about the limit existing sometimes when it equals the same kind of infinity from the left and the right, but that's really not correct to do that. We know what we mean when we say that, but that's not going to be something where the limit exists and we have a continuous function when L here is going to be plus or minus infinity. So remember that for the sake of continuous functions, L has to be finite. So our three-part definition here is going to be part one, and I'm going to use little Roman numerals, f of, and I'm going to use A exists, and then part two is going to be limit as x approaches A of f of x exists, and if both of them exist, then part three is the limit as x approaches A of f of x equals f of A. Let's take a look at what that might look like here. Let's just have a function here, f of x, and we're going to pick an A value here, and we'll call this point here a f of A, and this function is continuous at this point, not because I can draw that part of the graph without picking my pencil up off the paper, but because the limit from the left equals the limit from the right is equal to the function value. So f of A exists, the limit exists, and they're the same thing. We've seen several examples of continuous functions at this point. In the case of continuity, the more interesting dynamics occur at points where the function is not continuous at a point, at points of discontinuity, and we're going to talk about why. So there's going to be different types of discontinuities that we're going to talk about. Discontinuity with a hole, and this is going to be the only type of removable discontinuity. These other two will be non-removable. There's going to be a fourth type that we'll talk about later. But for right now, we've got holes, we've got jumps, and we have vertical asymptotes. Okay, so consider this graph here, and we have a issue where the limit exists and the point exists, but they're not the same thing. So we can redefine at a single point. What we would have to do here is we would have to say, well, the limit here is equal to, I assume that that limit is supposed to be 1. Limit of g of x, it's g of x, as x approaches 3 from the left is equal to 1. Limit of g of x as x approaches 3 from the right is also equal to 1. So we want the function value to be 1 instead of 5. So we're going to, g of 3 is currently equal to 5. Got the 0.35 here. We want to redefine g of x so that it equals whatever it equals to. This function here, when x is not equal to 3, and we want it to be equal to 1 when x equals 3, and we want to move that point down here and plug up this hole. That's how we're going to fix a point discontinuity. It's fixable, right? So you might say, well, what gives us the right to go around and redefine things? Well, we're just saying we can. We're not saying that we should all the time, but we're just saying, you know, this function might actually look this way, but this discontinuity is fixable because we can either, if that point wasn't there, we can define the point to plug up the hole, or we can just redefine this point and move it down here to plug up this hole. Now, sine of x over x just looks awful. It looks like this. It has a hole here, and it comes down here and comes down here, and then it starts oscillating but it gets like this, and it's like this. And we just need to know what is going to happen for sine of x over x as we get close to 0. And this is just a rule that we need to memorize. The limit as x approaches 0 of sine of x over x is equal to 1 because there's this hole here at 0, 1. Know this rule, okay? So we also need to know that limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. This is going to work as well this way, and this is going to work as well this way. But I can't take the reciprocal of this one because the reciprocal of 0 is going to be undefined. I can take the reciprocal of 1, and I'm still going to get 1. So doesn't matter whether I'm coming at this from the left or the right, I'm going to get close to 1. Limit as x approaches 0 from the left, sine x over x is 1. Limit as x approaches 0 from the right of sine x over x is also 1, but f of, if we call this f of x, f of 0 is undefined. So f of x is not continuous at x equals 0. I just want to make sure we talked about these special trig limits because we haven't talked about them in our discussion of limits so far, and they are important for you to memorize. So let's consider the piecewise function x equals, or y equals 1 if we're between 0 and 1, not, let's see, 0 and 1, and then 2 if we're between 1 and 2, and then 3 if we're between 2 and 3, and so on. So this is 2, this is 3, this is 1, and this is 0. Okay, so where is it going to be discontinuous? It's going to be discontinuous at 1, 2, 3, so on. It's going to be discontinuous because those limits are not going to exist there. So discontinuous at x equals 1, 2, and 3. Recall the negative power function. F of x equals 1 over x and g of x equals 1 over x squared. So let's think about f of x equals 1 over x at x equals 0. We have a vertical asymptote there. I think you knew that about the reciprocal function. That it looks like this. So it's going to be discontinuous at x equals 0 because the limit of f of x as x approaches 0 from the left is equal to negative infinity. You could also say because the limit as x approaches 0 from the right of f of x is equal to positive infinity. Either of those are not finite number L's. Finite numbers L, the limit does not exist there. Because the limit does not exist, it violates rule 2, but also f of 0 is undefined, which violates part 1. So it's all bad there for that one. Let's think about a fourth example here. F of x equals 1 over x plus 4 minus 9. And we're going to have a vertical asymptote at x equals -4. So it's going to be discontinuous at x equals -4. It'll be continuous everywhere else. So when we define continuity at a point, we create the checklist for determining continuity at the point, and we've already been doing that based on the patterns we see above. Detailing the 3 different types of discontinuities, we can create the following checklist to determine if a function is continuous. A function f is continuous at x equals a if the limit of f of x as x approaches a equals f of a. So part 1 of the definition, f of a is defined. Part 2, the limit exists as x approaches a, both from the left and the right. And part 3, the limit is equal to the function value. So I've been doing 1, 2, and 3 with Roman numerals. We have 1, 2, and 3 here without Roman numerals. It's the same thing. So determine whether or not the following functions are continuous at the given point x equals a. If not, state the condition on the continuity checklist that is violated. So the function is not going to be defined at x equals 1 because 1 is not in the domain, since 1 minus 1 is going to be 0. So I don't even have to do anything there to say continuity checklist number 1 is violated, since f of 1 is undefined. Don't even need to go any further. If I do want to go out here, though, I can say that if I stick 1 in here, I'm going to get 6 over 0. So there's going to be a vertical asymptote at x equals 1. Because I'm not getting 0 over 0, I'm not going to get a whole. So what type of discontinuity is this? Let's, like I said, just keep going. F of 1 is equal to 3 times 1 squared plus 2 times 1 plus 1 over 1 minus 1 is 3 times 1 plus 2 plus 1 over 0. 3 plus 2 plus 1 over 0 is 6 over 0. Since I get a non-zero number over 0, this is a vertical asymptote. If I got 0 over 0, would be a whole. Right? So let's think of this option now. F of x is equal to same thing. Let's see if we can factor this 3x squared plus 2x plus 1 over x minus 1. Are there factors of 3 that sum to 2? There are not. Factors of 3 are 3 and 1, and 1 and 3. We could get -3 and +1, but -3 and +1 don't multiply to give me a +3. -1 and +3 add to give me 2, but they would multiply to give me a -3, so that doesn't work. So we're going to have to use the quadratic formula if we want to think about factoring that, and that's just really not to our advantage to do that. So we're just going to instead let's look at a different, or let's go ahead and just see what happens here. If I say x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Let's just look at this discriminant part right here. b squared minus 4 times 3 times 1. Since our a was 3, our b was 2, and our c was 1. This is 4 minus 12 is a negative 8. And so we're going to get a negative inside of the square root. That gives us imaginary complex answers. That means it's not factorable across the real numbers. We don't want to deal with complex numbers in this class. So we're not going to be able to factor out an x minus 1 and get an answer here for it. So don't worry about that. That means x minus or x equals 1 is a vertical asymptote because there's no term in the numerator that helped cancel out the x minus 1. If we have f of x is equal to x squared when x is greater than or equal to 1 and is equal to x cubed when x is less than 1, then we get something that looks like this. 1, we have 1, 1 for both of them. We also have 0, 0. This is x cubed, so it's going to be a little bit more down here. And then this is going to come off this way and go up like that. And this is going to turn down like this. And it grows more in that direction. So this actually just decelerates a little bit. It goes from being cubic to being square, like that. But it does connect and has the same limit from the left and from the right. So, and the function value does exist. So limit of x squared as x approaches 1 from the right is equal to 1. Limit of x cubed as x approaches 1 from the left is also equal to 1. F of 1 is equal to 1 squared is equal to 1. All these things match each other. So f of x is continuous at x equals 1. Let's find the value of a for which this function is continuous at x equals negative 1. So let's find the limit from the left and the limit from the right. So negative 1 squared minus 2 times negative 1 is going to be equal to a times negative 1 cubed minus 9. So this is going to be 1 plus 2 needs to be equal to negative a minus 9. 3 is equal to negative a minus 9. 12 is equal to negative a, and a is going to be negative 12. Let's determine whether the following functions are continuous at x equals a. So let's look at this. X minus 1, x minus 3, x plus 1, x minus 1. Well, we have a problem here that we're not going to be continuous at 1 or negative 1 because 1 and negative 1 are not in the domain. Discontinuous at x equals 1 because there's a hole in the graph there. Discontinuous at x equals negative 1 because there's a vertical asymptote there. So Let's define continuity on an interval using continuity rules. If f and g are continuous at a point x equals a, then the following functions are also continuous at x equals a. The sum f plus g and f minus g will be continuous. A constant times f, where f is any constant, will be continuous. The product f times g and the quotient f divided by g will be continuous provided that g is not equal to 0, and f to the n, where n is a positive integer, not a negative integer, will also be continuous. Those are rules of what we know. Let's consider some functions now. F of x equals x and g of x equals x squared. Both are continuous everywhere from negative infinity to infinity. So based off of our rules up here, does that mean that 3 times f of x or 3x is also continuous? Yes, it is. That's rule number 2. Yes, rule number 2. How about f of x plus g of x? What about x plus x squared? Is that continuous? Yes. That's rule number 1. How about f of x divided by g of x? Be careful here. Continuous everywhere except x equals 0, because that's where x squared is going to be 0, and we can't divide by 0. So we'll say that it's continuous from negative infinity to 0, union 0 to infinity. And we'll express our interval of continuity as in interval notation here. Polynomial is continuous on its entire domain. Its entire domain will be negative infinity to infinity. A rational function will be piecewise continuous on its entire domain. We're going to remove any vertical asymptotes or places where holes occur. So let's state the interval of continuity for the following. F of x is equal to x squared minus 7x plus 12. Don't even need to think about it. It's a polynomial. It's continuous from negative infinity to infinity. Let's factor this. X minus 3, x minus 4. We're going to have this be continuous from negative infinity to 3, union 3 to 4, union 4 to infinity, because that's the domain of that rational function. Call the following example from an earlier video. And x squared minus 6x plus 8 over x squared minus 4, limit as x approaches 2. Remember that we needed algebra to simplify this, and we turned this into x minus 8, x plus 2. We had x plus 2 times x minus 2, limit as x approaches 2, and that should be a negative 2 there. X plus 2, those cancel, and this gave us negative 6 over 4 is a negative 3/2. So that allowed us to find the hole there at for that function. And I feel like I did something wrong here. Yes, this is a 4, not an 8. Negative 1/2. There we go. So that means that this was a negative 1/2, and that gave us a hole at 2, negative 1/2. Now consider going to negative 2. And we don't need to cancel out that factor, but it doesn't hurt us to do it. So that's going to give us -6 over 0, and we're going to say, uh-oh, we have a vertical asymptote there because we have k over 0. So we're going to need to look at the graph here. We're going to say at -2, and we have a horizontal asymptote here at 1, and we have 1, 2, 3, 4, and we have a y-intercept of -2. And then we have another piece that's going to be up here. And so we see this vertical asymptote here with going down to -infinity from the right and up to +infinity from the left, I think is what's going on. Let's see if that's right. X -4 negative over positive is negative. Yeah. Okay. So we have a asymptote, a vertical asymptote at x equals -2. Right. Let's keep going here and determine continuity or define continuity on an interval and discuss continuity of a function composition. So f of g of x, also written as f of g of x, we want to have specific functions f and g. We want to apply this concept in general. So let's determine the interval of continuity for f of g of x when f of x is equal to x squared plus 1 and g of x is equal to 2x plus 3. So let's find that f of g of x is equal to 2x plus 3 squared plus 1 is 4x squared plus 12x. 12x plus 9 plus 1 is 4x squared plus 12x plus 10. That's going to be continuous everywhere. F of x is continuous on -infinity to infinity, and g of x is also continuous on -infinity to infinity. And look at that, the f of g of x is also continuous on -infinity to infinity. Interesting. F of x here is continuous on 0 to infinity. Actually, it's only continuous on the open interval 0 to infinity. G of x is continuous on -infinity to infinity. F of g of x is the square root of x minus 3. And so f of g of x is going to be continuous on 3 to infinity. I don't see how we get that from there with a general rule, but let's see what our theorem says. So if g is continuous at x equals a and f is continuous at g of a, then the composite function f of g of x is equal, that's f of g of x is continuous at x equals a as well. That's just at a point, right? So the limits of composite functions, if g of x is continuous at x equals a and f is continuous at g of a, then limit of f of g of x as x approaches a is f of limit of g of x as x approaches a. Since it's continuous there at g of a, then we'll go ahead and replace that limit with g of a, and we'll find f of g of a, and that will be our limit value for our composition. If limit of g of x as x approaches a equals L, and f is continuous at L, then limit as x approaches a of f of g of x equals f of limit of g of x as x approaches a of replaced with L is f of L. Basically the same rule, but just written two different ways. So let's go ahead and see if this limit exists here as x approaches 0. If it does, then we can stick that limit in and raise it to the 10th power. So we're going to say that this is going to be all of those things with x's are going to become 0. And I'm going to be left with 2 over 1. And that's going to be 2 to the 10th power. So our f of x here is equal to x to the 10th. Our g of x is equal to x to the 4th minus 2x plus 2 over x to the 6th plus 2x to the 4th plus 1. Check that. Yes, that works. That gives us our composition. And we're going to say now that g is continuous at 0. So we're going to find g of 0. G of 0 is going to be 2 over 1 is 2. So then the limit of f of g of x as x approaches 0 is going to be 2 to the 10th is going to be big number. Trying to remember what that is off the top of my head, but it is, let's see, 2, 4, 8, 16, 32, 64, 128, 256, 10, 512. It's this one, 1024, I think. 1, 2, 4, 5, 6, 7, 8, 9, 10. Yeah, this is 1024. Right? Use the above theorem to evaluate. Oh, I just did that. So, yep, just did that up above. Is the function continuous at x equals 0? Yes, it is. Limit as x approaches 10 of f of x equals 1024. F of 0 originally would also be 1024. So since the limit is equal to the function value, it is continuous there. Another question here before we go on is the function f of x equals the square root of x continuous at x equals 4. Yes, it is, because f of x equals the square root of x is continuous on the domain of 0 to infinity, like that, on that entire interval. It's not continuous at its vertex at 0, but it's continuous everywhere else where it has behavior from the left and the right. Let's keep going here. Continuity on an interval. A function f is continuous from the right, called right continuous at a. If the limit of f of x as x approaches a from the right equals f of a. A function f is continuous from the left, called left continuous at x equal of at a if limit of f of x as x approaches a from the left is equal f of a. This right continuity, left continuity is where some books talk about the square root function being continuous at 0. So you can talk about the square root function being right continuous. And so right continuous at x equals a. An example here would look like this. Maybe this point is there, maybe it's not. It doesn't need to be there. Actually, it does need to be there. It needs to be an endpoint there. So we have a f of a and I only have behavior coming from the right. So this is right continuous. It's not going to be right continuous if I have a hole here. This is not right continuous. Okay, so left continuous at A is going to look something more like got this, and we have a f of A like that. Limit as x approaches A from the left of f of x is equal to f of A. If left-wise continuous, again, if we have a hole over here, and then it's not going to be left continuous. If we have a f of A sitting up here, for instance, that would be bad. But to have continuity, you need to have the function value equaling the left-hand limit. All right, continuity on an interval. A function f is continuous on an interval I if it is continuous at all points on I. If I contains endpoints, like I is the interval 1, 4. Continuity on I means f is continuous from the right and left at the appropriate endpoint. So this is where you get into that with the domain of the square root function being 0 to infinity, and it has an endpoint over here, and you say, well, since it has a left endpoint, it only needs to be right continuous there, and then it's continuous on its entire domain. So I'm just telling you what other books say. For us right now, we're going to say that the square root function is not continuous at x equals 0 because the limit doesn't exist because it doesn't have behavior from the left and the right. But you can get this definition here of continuity on an interval with the domain being written in interval notation, and ask your teacher what they want you to do. So for all x equals A, you need to have f of A exists. The limit of x approaches A of f of x exists, and the limit of f of x as x approaches A equals f of A, your continuity checklist. But then 4, we're going to say that it's left continuous at the left endpoint, and then it's going to be right continuous at the right endpoint. And this is backwards. It's going to be right continuous at the left endpoint. It's going to be left continuous at the right endpoint because you need to come from the right on the left side. You need to come from the left at the right side. So just look at the graph. So, yep. So let's look at the function g of x and the function ln of x here. And g of x is equal to e to the x. We've looked at that one several times. We have ln of x here. And intervals of continuity for e to the x. E to the x is continuous on negative infinity to infinity. Ln of x is continuous on 0 to infinity. Is f of x equals ln of x continuous at x equals -2? No, it's not defined at x equals -2. Continuity of inverse functions. If a function f is continuous on an interval I and has an inverse on I, then its inverse f inverse of x is also continuous on its domain. So let's just look at trig functions here. So all trig functions are continuous on their domain, and the domain of sine is going to be negative infinity to infinity, cosine negative infinity to infinity. Tangent of x is going to be everywhere other than the zeros of cosine. So that's going to make us eliminate all of the odd multiples of pi over 2. So x such that x is not equal to 2k plus 1 pi over 2. Okay, let's determine the values of x for the following function. Where is it undefined? So the question there is basically where is e of x equal to 0? I'm sorry, equal to 1. And that happens at x equals ln of 1, which is equal to 0. So our interval of continuity is going to be negative infinity to 0, union 0 to infinity. 0 is our only bad point. Okay, another example here, or 2. F of x is going to be equal to x to the 4th minus 3x squared minus 2x plus 1. What's the interval of continuity? That's a polynomial. So that's going to be continuous on the entire real number line. Example 2 here, f of x is equal to x squared plus 2x plus 7 over x minus 1. And that is going to be discontinuous, or it's going to be continuous on its entire domain, which is everywhere other than x equals 1. So negative infinity to 1, union 1 to infinity. So let's go ahead and look at functions involving roots. Continuity of functions involving roots. Assume n is a positive integer. If n is an odd integer, then the nth root of f of x is continuous at all points for which f of x is continuous. If n is an even integer, then the nth root of f of x is continuous at all points for which f of x is continuous, and f of x is greater than or equal to 0. For which values of x are the actually, we're not going to say equal to 0 because that would be the vertex, and we've defined that it's not continuous there. It's only continuous from one direction. So yeah, we'll say greater than 0. For which values of x are the following functions continuous? So we're going to say 0 to infinity there. We're going to say negative infinity to infinity here. We're going to say negative 3 to infinity here. And we're going to have to look at this graph probably here to say what does that look like. So that's the top half of this circle here. And we're continuous between negative 3 and 3, neither endpoint included. So let's look at this one. This is an even inside of an odd here, like this. So this is the cube root of x squared minus 2x plus 4 squared. So there's no problem spots from this one. That's continuous everywhere because it's a polynomial. So we're going to get an interval of continuity from negative infinity to infinity, since this was continuous everywhere. That cube root will also be continuous everywhere. Let's go ahead and look now at f of x is equal to the square root of x squared plus 2x plus 7 over x plus 1. Remember that the square root has to be greater than 0, so x squared plus 2x plus 7 over x plus 1 has to be greater than 0. So we need to look at that on a sign chart if we can. Let's do this. I'm going to complete the square here, x plus 1 squared plus 6. Yeah, that doesn't help me. Greater than 0, I was going to say if this could give me some answers to the quadratic formula. So that top part is always going to be positive, no matter what the value of x is. I can never make it negative. So this is going to depend completely on the denominator here. And that's going to be -1. And when we're to the left of that, this is going to be negative. And when we're to the right, it's going to be positive. And greater than 0, we want positive. Positive over positive is positive. It's not going to be defined to x equals 1. So my domain and the interval over which it's continuous is going to be 1 to infinity. If I could have factored the numerator, and let me give you an example of that, x squared minus 4 over x plus 1 would be x plus 2, x minus 2 over x plus 1. I'd be interested in -2, +2, and a -1 would all be zeros, and they would all be negative on this side. A negative times a negative divided by a negative would be a negative, so the graph would not exist here because I'd be taking the square root of a negative number. I cross that boundary and this one becomes positive. Negative and negative is positive, so I'm okay. Let's see. I'm okay here, not okay here, and I'm okay here. I'll pick something like 0 here. That's going to be a negative over positive is negative, and it's not going to exist in here, but it's going to exist up here. Now, as far as that's where it's defined for its domain, is going to be -2 to -1 union 2 to infinity, but it's continuous on the open interval -2 to -1 union 2 to infinity. We need to be continuous on open intervals like that. All right, that's it for this video. And when we come back next time, we'll start introducing the derivative. See you for the next video.